A telescope in Chile is now generating 7 million alerts a night, capturing a brand new full-resolution image of the sky roughly every 40 seconds, and it just released a view of one of the most heavily studied patches of space in the world that lines up directly against Hubble, Webb, and 2 other major observatories at once. Stick around, because this is not the same story you may have already heard about this telescope. This is what's happened since and what's happening right now, as its real 10-year mission has finally, fully begun. And hit subscribe now, because this channel breaks down real published research without the exaggeration, and you do not want to miss where this story goes next. Before anything else, let's be honest about the timeline, because that matters here. The Vera Rubin Observatory did not do something 8 minutes ago. What it has done is spend the past year moving through a series of genuinely major milestones. First light imagery, an alert system test, and finally, this past July, the true start of its actual 10-year survey mission. And in just the last day, according to a report from phys.org, the observatory released a striking new deep-field view of one of astronomy's most famous patches of sky. This video is about that full arc, because the most recent chapter genuinely does not make sense without the ones that came before it. Quick recap. For anyone who hasn't already heard how this observatory works, the Vera Rubin Observatory sits atop Cerro Pachon in Chile, home to the Simone Survey Telescope and the LSST camera, the largest digital camera ever built for astronomy, capturing images at 3,200 megapixels each. Unlike most major telescopes, which stare intensely at one small patch of sky for a long time, Rubin was built to do the opposite, repeatedly photographing the entire visible sky, over and over, every clear night, for a full decade, building what officials have called the greatest cosmic movie ever made. To understand why that combination is such a big deal, it helps to compare Rubin against the major sky surveys that came before it. Earlier large-scale efforts, like the Sloan Digital Sky Survey, which spent years methodically mapping large portions of the northern sky starting in the early 2000s, fundamentally reshaped modern astronomy by making enormous amounts of standardized sky data publicly available for the first time. But those earlier surveys generally worked through a region of sky once, or returned to it only occasionally, producing something closer to a detailed still photograph of the universe rather than a moving picture. Rubin's 4-meter primary mirror, combined with a field of view spanning roughly 10 square degrees in a single exposure, an area of sky many times larger than what most major telescopes can capture at once, allows it to repeatedly revisit the same regions again and again across a single survey, something earlier generations of sky surveys were never designed to attempt at this scale. That difference, a single detailed map versus a continuously repeating one, is exactly what makes Rubin capable of catching things that appear, disappear, or change, rather than only cataloging what simply sits still. If you're the kind of person who wants stories explained clearly instead of buried under jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. The first big milestone after those original first-look images came on February 24th of this year, when Rubin tested its automated alert system for the very first time. According to Stephen Smart, an astronomer at the University of Oxford, who serves as scientific lead for one of the systems built to process this data, the observatory photographed a single patch of sky for which previous observations had already built up a detailed reference template. By comparing each new image against that template, the system was designed to automatically flag anything that had changed, appeared, or disappeared between exposures. In that single test night, according to reporting on the milestone, Rubin's system generated 800,000 individual alerts, each one representing some kind of genuine change, detected somewhere in that single patch of sky. That was still just a test. According to project officials, once the observatory's full 10-year survey formally got underway, that number was expected to grow dramatically, and it did. Officials have described Rubin, once running at full capacity, as capturing a new, detailed image approximately every 40 seconds, all night, every clear night, and generating roughly 7 million alerts and 20 terabytes of fresh data in a single night alone. To put that in perspective, that means Rubin is now capable of flagging something that changed in the sky somewhere in its field of view, an average of well over 80 times every single second the observatory is running. Here's the detail that tends to stop people once they hear it laid out plainly. According to CNN's coverage of the milestone, the observatory's full legacy survey of space and time had originally been expected to begin by early 2026, but additional equipment checkouts pushed that timeline back. The full survey formally got underway this past July, meaning as of right now, Rubin has only been running its actual 10-year mission for a matter of weeks, and it is already producing results at a scale that has genuinely surprised even the scientists who spent decades building it. It's worth pausing here to explain how a single observatory could possibly keep up with a fire hose of information this large, because the answer says a lot about how modern astronomy actually works now. Rubin itself does not sit alone processing all of this data in isolation. According to Stephen Smart, the alerts generated each night get distributed out to a small number of organizations called data brokers, 7 of them in total, including systems like the one Smart himself helps lead, called Lasser. Each broker applies its own filtering and classification tools to sift through that nightly flood, flagging the alerts most likely to represent a genuine supernova, a newly discovered asteroid, or some other significant transient event, and passing those refined results along to research teams and automated follow-up telescopes around the world. In effect, Rubin functions less like a single all-seeing eye, and more like the trigger for an entire global relay network of astronomers and automated systems, all working together to catch fleeting cosmic events before they fade. This entire structure exists because of a basic, unavoidable problem in modern astronomy. Many of the most scientifically valuable cosmic events, a supernova in its earliest hours, an asteroid on a genuinely concerning trajectory, a star's brightness flickering in a specific pattern tied to an orbiting planet, are only useful to study if they're caught quickly, often within hours or days of when they begin. A telescope that only checks a given patch of sky once every few weeks or months, the norm for most of astronomical history, will inevitably miss the vast majority of events like this entirely, or catch them too late for the most valuable early data to still be recoverable. Rubin's entire design, repeatedly revisiting the same patches of sky, comparing each new image directly against everything captured before it, and issuing alerts within roughly a minute of detecting a change, exists specifically to close that gap. According to figures released by the National Science Foundation in the weeks following the survey's true start, in just about a month and a half of early operations, Rubin had already discovered more than 11,000 previously unknown asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects, small, distant bodies orbiting far beyond Neptune, the same general region of space where scientists continue debating the existence of a hypothetical undiscovered planet. That 11,000 figure represents a massive jump beyond the original 2,104 asteroids identified during the observatory's brief first-look test period roughly a year earlier. And officials have stated that Rubin alone is expected to discover millions of new asteroids within just the first 2 years of its full survey. Buried inside that growing catalog of newly discovered objects is a genuinely remarkable individual find. Among the roughly 1,900 asteroids identified during Rubin's original first-look testing period is one cataloged as 2025 MN45, a small main belt asteroid measuring less than a kilometer across. According to follow-up analysis of its behavior, this asteroid completes one full rotation on its own axis in approximately 88 minutes, making it, as of current records, the fastest known rotating asteroid of its size ever identified. For comparison, most asteroids of a similar size typically take anywhere from several hours to multiple days to complete a single rotation. An object spinning that rapidly is right up against the theoretical limit where centrifugal force should begin tearing a loosely bound rocky body apart, making it a genuinely valuable natural laboratory for studying exactly how solid asteroids of this size are held together in the first place. It's a small, easy-to-overlook entry buried in a catalog of thousands, and precisely the kind of unexpected, individually fascinating discovery that a survey this broad is uniquely positioned to stumble across almost by accident. There's a second capability tied to the same real-time alert system that doesn't get nearly as much attention as the asteroid counts, but that researchers involved in the project consider just as significant. According to NSF officials, Rubin's alerts are expected to help scientists catch the faint visible light associated with sources of gravitational waves and neutrinos, 2 entirely different kinds of cosmic signals detected by completely separate instruments here on Earth. Gravitational wave detectors that sense ripples in space-time itself from events like colliding neutron stars, and neutrino observatories that catch nearly massless particles streaming in from violent cosmic events elsewhere in the universe. When either of those instruments detects something significant, astronomers often have only a narrow window of time to figure out exactly where in the sky that signal came from, and to point other telescopes there quickly enough to catch any visible light counterpart before it fades. Rubin's ability to repeatedly and rapidly scan enormous sections of sky makes it an unusually well-suited tool for exactly this kind of urgent, multi-instrument follow-up work, sometimes called multi-messenger astronomy, where a single cosmic event gets studied simultaneously through several completely different types of signals at once. The planetary defense implications of the same real-time system are worth spelling out plainly, too, because they matter well beyond scientific curiosity. Every one of the near-Earth objects Rubin identifies gets added to a growing global catalog of asteroids, whose orbits are precisely tracked, allowing astronomers to calculate, often decades in advance, whether any of them pose a genuine future risk of colliding with Earth. According to researchers involved in this specific area of Rubin's mission, the greatest actual danger from asteroid impacts historically hasn't come from the relatively small number of hazardous objects we already know about and can track confidently. It has come from the ones nobody has found yet. A telescope capable of systematically imaging the entire visible sky every few nights, rather than relying on the more limited, irregular coverage older survey telescopes could manage, represents one of the most significant single improvements to that early warning system in the history of the field. If you have found this as interesting as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. It's worth taking a brief moment to recognize just how long a project like this actually takes to build, because the payoff happening right now didn't come together overnight. According to NOIR Lab, astronomer Tony Tyson of the University of California, Davis, whose original scientific vision helped lay the foundation for what eventually became the Rubin Observatory, was named to the 2026 Time 100 list, Time magazine's annual recognition of the 100 most influential people in the world, specifically cited for his pioneering contributions to cosmology and his decades of leadership in advancing this exact survey. That recognition reflects a genuinely important detail about how a project like this actually comes together. Rubin is the product of more than 2 decades of planning, engineering, fundraising, and construction, jointly funded by the National Science Foundation and the Department of Energy, and jointly operated by NOIR Lab and the SLAC National Accelerator Laboratory, involving thousands of scientists and engineers across dozens of institutions over that entire span. The $800 million facility, now generating headlines for its asteroid discoveries, represents the tail end of a project that began taking shape long before most of the researchers currently analyzing its data had even finished graduate school. Now, to the part of this story that's genuinely brand new. According to a Pheasant.org report published within the last day, Rubin has released a striking new data product built around a section of sky known as the cosmos field, one of the most intensively studied patches of space anywhere in modern astronomy. What makes this particular release significant is not simply that Rubin photographed this region, but how it fits alongside everything that's already been gathered there. According to the report, this new release overlays Rubin's exceptionally deep observations of the cosmos field directly against the footprints of several other major surveys of the exact same patch of sky, including observations previously gathered by the Hubble Space Telescope, the James Webb Space Telescope, the Chandra X-ray Observatory, and the Spitzer Space Telescope. Together, these nested, overlapping surveys mean that this single small region of sky now has more layered, cross-referenced observational data available than almost anywhere else in the observable universe: visible light from Hubble, infrared detail from Webb and Spitzer, X-ray data from Chandra, and now Rubin's own wide, repeated time-lapse observations layered directly on top. According to the same report, this release represents an early phase of a larger, ongoing data product, with a second phase expected to arrive later this year, adding individual processed images, difference images that isolate exactly what has changed between observations, and the reference template images those comparisons are built from. In practical terms, this means researchers studying this specific patch of sky will increasingly be able to combine Rubin's wide, repeated time-lapse view of the region with the extraordinarily fine, deep detail already captured there by some of the most powerful telescopes ever built, a genuinely unprecedented combination for any single patch of the observable universe. There's another category of object this same design makes Rubin unusually well-suited to catch, and it connects to one of the more genuinely exciting open questions in modern astronomy. In all of recorded history, astronomers have only ever confirmed 2 objects that formed around a different star entirely and simply happened to pass through our own solar system on their way through the galaxy: 1I Oumuamua, spotted in 2017, and Comet 2I Borisov, discovered in 2019. Both were found only after they had already entered our solar system, leaving researchers relatively little advance warning and limited time to study either one closely before it moved on. Because Rubin repeatedly scanned such an enormous share of the visible sky, comparing each new image against a growing archive of everything captured before it, researchers involved in the project have described it as the single most capable tool ever built for catching exactly this kind of rare interstellar visitor, potentially spotting future examples earlier, and identifying considerably more of them over the coming decade than has ever been possible with any previous generation of telescope. Picture for a moment exactly what it means for a research team studying a distant, faint galaxy sitting somewhere inside that cosmos field right now. A scientist could pull up Hubble's sharp visible light image of that galaxy structure, layer Webb's infrared data to see through any obscuring dust and study its older, cooler stars, check Chandra's X-ray data for any sign of an active black hole buried at its center, and then, for the first time, Add Rubin's own repeated wide-field observations to track whether anything in or around that galaxy has changed, brightened, dimmed, or exploded over the following days, months, and years. No single observatory built before now could offer all of that, layered directly together for the same small patch of sky. That's the genuinely new capability this latest release represents. Picture, for a moment, the sheer scale of what this project will have accumulated by the time its 10-year survey actually concludes, because the numbers involved are difficult to hold in your head all at once. If Rubin is currently generating somewhere in the neighborhood of 20 terabytes of raw data on a single productive night, and continues operating at that pace across a full decade of nightly observations, the observatory is expected to accumulate a total data set reaching into the hundreds of petabytes by the time the survey wraps up, an amount of astronomical data that dwarfs the combined output of essentially every ground-based optical survey telescope that came before it. Officials involved in the project have described the eventual full catalog as including detailed measurements of roughly 20 billion individual galaxies, alongside tens of billions of individual stars within our own Milky Way, and millions of solar system objects, asteroids, comets, and potentially new large bodies in the outer solar system, all captured repeatedly across that same 10-year span. No single research team, and arguably no single country's worth of astronomers, could realistically analyze a data set that size entirely on their own, which is exactly why Rubin's data is being structured from the outset for open, distributed access by the global research community, rather than kept within any single institution. It's also worth connecting this back to the two biggest, most talked about open questions this observatory was specifically built to help answer. According to NSF officials, Rubin's 10-year survey is expected to produce critical new data toward understanding dark matter and dark energy, the invisible components that, according to current cosmological models, together make up the overwhelming majority of everything in the universe, despite never having been directly detected or observed. By repeatedly and precisely mapping the positions and subtle gravitational distortions of billions of galaxies across the entire visible sky over a full decade. Researchers expect Rubin to provide one of the most detailed and statistically powerful datasets ever assembled for testing current theories about exactly how these mysterious components shape the structure of the universe. This is, according to the researchers who spent over 2 decades helping design and build this facility, arguably the single most important long-term scientific goal behind the entire project. Even more so than the already remarkable asteroid discoveries making most of the headlines so far. It's worth being honest, too, that Rubin is still extremely early in its actual full survey. A 10-year mission that has been fully running for only a matter of weeks has, by definition, produced only a tiny sliver of the total dataset it will eventually generate. Officials involved in the project have been careful to describe current results as an early preview rather than anything close to the observatory's full scientific output. And researchers across dozens of institutions worldwide are still actively building the analysis tools needed to properly sift through the sheer volume of data the telescope is now producing every single night. Some of the most significant discoveries hiding somewhere inside Rubin's nightly flood of alerts may not be identified by researchers for months or even years after the data was originally captured, simply because there is, quite literally, more new information arriving each night than any research team could fully process in real time. So, what does all of this actually add up to? The Vera Rubin Observatory's story didn't end with its first dramatic reveal back in 2025. If anything, that was only the opening scene. In the time since, it has quietly built and tested a real-time alert system capable of flagging tens of millions of changes across the sky every single night, formally launched its true 10-year survey mission this past July after some additional delays, pushed its asteroid discovery count past 11,000 and counting, stumbled onto individually remarkable finds, like the fastest-known spinning asteroid of its size, and, just within the past day, released a new, deeply layered view of one of the most important patches of sky in modern astronomy, built directly on top of data from Hubble, Webb, Chandra, and Spitzer combined. None of this happened 8 minutes ago. It happened across a carefully planned multi-year rollout more than 2 decades in the making, and the genuinely remarkable part is that the mission producing all of it has barely even started. There is something worth sitting with in that last point specifically. Every figure covered in this video, the 11,000 asteroids, the 7 million nightly alerts, the newly layered cosmos field data, comes from what officials themselves describe as an early phase of a 10-year commitment. The observatory has been running its full survey for a matter of weeks, out of a planned decade of continuous operation. If the opening weeks alone have already produced a record-setting asteroid, a real-time alert network processing tens of millions of events nightly, and a dataset layered directly against 4 of the most powerful telescopes ever built, it becomes genuinely difficult to predict what a full 10 years of that same pace might eventually reveal. That uncertainty isn't a weakness in the story. According to the researchers who spent over 2 decades building this facility, it's precisely the point. A survey instrument built to repeatedly and systematically watch the entire sky, rather than searching for one specific predicted answer, is designed from the ground up to catch the discoveries nobody thought to look for in the first place. Here's the detail worth sitting with as this video wraps up. Somewhere in Chile, right now, on any clear night, that same 3,000 kilogram camera is swinging across the sky roughly every 40 seconds, quietly building toward a final archive that will eventually include tens of billions of stars, roughly 20 billion galaxies, and millions of solar system objects, one methodical exposure at a time. Nobody, including the researchers running the project, can say with certainty what the single biggest discovery buried somewhere in that decade-long data set will eventually turn out to be. That, according to nearly everyone involved in building this observatory, is exactly the point of a survey instrument built this way. It isn't chasing one predicted answer. It's simply, patiently watching everything, night after night, for as long as it takes for the universe to show something nobody expected. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because Rubin still has roughly 9.5 years left on its survey, and there is a real chance the next update on this observatory is bigger than everything covered in this video combined. Thanks for watching, and I will see you in the next one.